So in the spring of 17, test 2, I decided to do it a little bit weird. Whereas I did rotational motion and then energy second. And what I found is it didn't work that well with the labs. So test 3 material for the summer, we did energy first, which is what they typically do in the labs, and then we move to rotation. So when you look at those tutorials, problem sets 1, 2, and 3, I was very faithful to the problem sets from the spring. Problem sets 4, 5, and 6, I kind of had to reassemble them so that they appeared to be more in order with what we're going to do in lecture. So what you need to do is, for those tutorials, look at all 3 of those tutorials for test 2 material, and then you'll be able to pick out the problems that you need. So it's a little bit, I know it's a little bit more cumbersome than what test 1 material is, but if you dig around enough, if you dig through fall's tutorials, spring tutorials, all those tutorials should give you enough to get the stuff done. Combination of YouTube and downloading the videos off my Google Drive will be it will be enough to get everything. Couple of reminders. One, this problem set technically is due Friday at 6 o'clock. We will have tutors from 1 to 6, so you can talk to them. If you want to turn in your homework at the end of the day, that's great. If you want to turn in your homework first thing on Monday, that's fine. I was in first thing on Monday, like 8 o'clock to 9. It's just that I have no promise that it will be graded in time for the test. So that's kind of the deal. Otherwise, let's start. When we have, what I'm going to do now is, I call it my Rosetta Stone. And we're all familiar with what the Rosetta Stone is. It was an artifact found in Egypt. And at the time, people never understood how hieroglyphs were read. And then this stone was found, and it had like ancient Greek hieroglyphs and something else. And it would allow the people to be able to translate. And so what I'm going to do now is illustrate how the linear world has a relationship with the rotational world. The linear world is what we've been studying for the last 9 days, objects moving through space. We never really considered much about its geometry. But now when we're rotating things such as, you've got a lazy Susan, you've got a merry-go-round on a playground, you've got if you've ever been a gravitron, we're talking about circular motion now. In the linear world, we have position, which we use as x, and then the standard unit that we use is meters. In the rotational world, we have angle, which is theta, and then we use either degrees or radians depending on the situation. For angles, we know that 360 degrees is equal to 2 pi radians. Now, I do write out radians technically radians are unitless. What I've found is that students, when it comes to angles, do prefer to have a unit of some kind. And technically, radians are unitless. So the true answer is not the angle is pi radians, but that the angle is pi. End of discussion. However, it is 2:13. You guys have only been studying this for 9 days. I'm very forgiving and understanding about this particular matter. In the linear world, we have velocity, which is v, which is in meters per second. And time, there is rotational time and linear time are the same thing. But for velocity, you have something called angular velocity. Oop, I can't spell. Angular velocity has a symbol, and it looks like that. It is a lowercase omega. That is the symbol. And it is usually in radians per second, or since radians are unitless, you can just write it as inverse seconds. Now, in both of these cases, v is dx dt, and omega is d theta dt. So the change in position with respect to time is velocity. The change in angle with respect to time is called omega. So this particular pin has no omega, but as it rotates, now it does. So the omega allows you to see how quickly that thing is spinning. We're familiar with acceleration. A, which is in meters per second squared, and A is dv dt. The change in velocity with respect to time is the linear acceleration, something we're very familiar about. This is angular acceleration. Angular acceleration is called alpha, a lowercase alpha, or lowercase a. Alpha units are in radians per second squared, or you could say seconds inverted squared. And so those are the relationships. And alpha is d omega dt. So we can see the associations between the linear world and the rotational world. And now we're going to have to talk about, in the linear world, we're familiar with mass, m, which is in kilograms. And now, building on our Rosetta Stone, we're going to have to pause and deal with the new term because it's a little bit different from what we've all said or dealt with for the last week. The rotational world. Rotational mass is called moment of inertia. And moment of inertia is I, and its units are kilograms meters squared. So rotational mass is known as moment of inertia. Now, one of the easiest demonstrations to do to talk about moment of inertia is if you have an object, actually I'm going to use this one. this bar is of uniform mass density. So it's the center of mass is basically at the middle of the object. And if I sit here and I rotate it like this, it's fairly easy to rotate. And so rotational mass, such as if you've got Newton's second law, F equals ma, the bigger the mass, the more force you have to put into it in order to get it to accelerate. Rotational mass is the bigger the rotational mass, the bigger the moment of inertia, the more rotational force, and we're going to get into that term in a little bit, the more rotational force that you have to put into this bar in order to get it to rotate. As an example, I haven't done anything to this bar, but now I'm going to try to rotate it with this around the end. It's way harder to get this thing to swing around. Now, another example will be, this is a clamp, just a simple clamp, and I'm going to put it in the middle of the bar. Now, if I rotate this assembly about the middle, it's fairly easy to rotate. Now, what I'm going to do is I'm going to take this bar and move the mass towards the end, put my hand at the rotation point, and it's kind of difficult to get this thing to rotate. Moment of inertia is based on two things. One, the mass itself, and two, the distribution of that mass. So the bigger the moment of inertia, and if, oh, heaven help me, the more rotational force I have to put into this in order to get this thing to swing around. So you have to look at the distribution of the mass and the mass itself. So let's now, for all objects in 213, we will be dealing with uniform mass density, i.e., center of mass is the center of the object. And since I'm thinking about it, I know it's a complete aside. Did y'all see Kevin Durant's three-point shot at the end of the game yesterday? That's physics. You understand? You've done two-dimensional motion. I could write an equation for that. It was amazing. So now back to the subject. All objects in 213 we will be dealing with uniform mass density. Center of mass is the center of the object. So if you have a stick, a 213 stick, the center of mass is the center of that stick, which means that if this is length L, then that length is L over 2, and that length is L over 2 as well. Simple. In 211, I would make the mass non-uniform and then let them do calculus, but since I'm not allowed to use calculus in this course, we can't do that. If you have a disk, that center of mass is dead smack in the middle of that disk. And so you can do it that way. There may be instances in the future where if you have a distribution of particles and I said, well, where's the center of mass of those particles? The center of mass of a system of particles is the weighted average. So you're going to have a weighted average of these systems of particles. Let's say for a moment that we had 3 particles, and the mass of each particle, let's say this one was 2, that was 1, that was 4, and they have their own coordinates, 1, 1, negative 2, 4, 0, and negative 5. So you have a 2 kilogram mass at 1, 1, a 1 kilogram mass at negative 2, 4, and a 4 kilogram mass at 0, negative 5. And I want to know is, well, what's the center of mass of that system? Take the weighted average. So we're going to take the weighted average, and you're going to do it in the x direction and the y direction. So x center of mass is the sum of this and I'll explain this in just a moment. Y center of mass is the sum of this. So what you're doing with this is you're taking a sum of the product divided by the sum. In English, this is m1 x1 plus m2 x2 plus m3 x3, however many particles you have, divided by m1 plus m2 plus m3. And now we plug in our numbers. 2, x1 is 1, 1, x2 is negative 2, m3 is 4, x3 is 0. And so we end up with, amazingly, that the x coordinate for the center of mass is 0. You do the same thing for the y coordinate. M1, 2, y1, 1, M2, 1, y2, 4, M3, 4, y3, negative 5. So 2 plus 4 is 6, minus 20 is minus 14. So my center of mass coordinates are 0, negative 14. And so you can figure out, if you have a system of particles, all you do is take the weighted average. Occasionally a problem creeps in where it gives you a list of these things and asks for the center of mass, and then you just have to do this. Now, getting back to the whole moment of inertia thing. Moments of inertia, we're going to keep things simple. We'll either deal with points, sticks, or you can think of them as bars, or discs, or circles. So the moment of inertia of these things, for a point, we have a mass at a given radius r, and it's rotating around a particular point. That particular moment of inertia, I, is mr squared, where m is the mass of the point R is the distance from the rotation point out to the mass, and then it's rotating around. For sticks, I is 1/12 ml squared. Now, for this particular equation, it's a stick rotating about its center of mass. For the disc, it's also rotating around its center of mass. It also has a radius r, and its moment of inertia is 1/2 mr squared. So those are our three types of geometric shapes that we will be using in this course. They will be given to you on the test. I don't expect you to memorize this stuff. If I expect you to memorize stuff, we'd be in organic chemistry or biology. This is physics. And so we have, if you had, let's say you had a stick. Its mass was 3 kilograms and its length was 2 meters. Its moment of inertia would be 1/12 ml squared, or 1/12 2 squared. Oh, I love this. I must be subconsciously making these numbers. 2 squared is 4, 4 times 3 is 12, 12 times 12 is 1 kilogram meter squared. And that's the moment of inertia of a 2 meter long, 3 kilogram stick rotating about its center of mass. Now, I showed you earlier in the demo, if I moved the rotation point of the stick, well, hold on. All right. If I move the rotation of the stick not at the center, but out at the end, the moment of inertia changes because the distribution of the particles change. For this, if that's the rotation point, the mass is still the same. The length is still the same. What's the new moment of inertia? The new moment of inertia is not going to be 1 kilogram meter squared. You're going to have to adjust for it. The way that you do this is to use the parallel axis theorem. A very complex phrase for a very simple equation. When you have an object that's not rotating, and you know how I hate writing stuff down, so if I'm actually writing it, it's important, is not rotating about its center of mass. Use so for this stick, the new moment of inertia is its regular moment of inertia about its center of mass plus md squared. So this moment of inertia, and we're going to get to all the parts, is its normal center of mass 1/12 ml squared. This m is the mass of the object that's rotating. That m is the same as that m. The d is the distance from the center of mass to the point of rotation. So if you have an object, length L, center of mass is there, rotation point is there. What is that length right there? L over 2. It's half the length of the bar. If I put it here, you would just measure the distance from the rotation, or if I put the rotation point here, then it would be L over 4. If I put it over here, it would be L over 4. If I put it out there, it would be L over 2. It's that simple. That D is the distance from the rotation point to the center of mass. It doesn't matter where it's rotating, that distance, D, is always from the center of mass to the rotation point. So that makes this L over 2 squared. So 1/12 ml squared plus 1/4 ml squared. Common denominator of 12. So actually I can factor out the ml squared. ml squared 1/12 plus 1/4 ml squared 1/12 plus 3/12 ml squared 4/12 or 1/3 ml squared. And so that is the moment of inertia of a stick. And you can see that it increased from 1/12 to 1/3. So the moment of inertia does go up. Yes?
I thought it was L over 2. Where did the 1/4?
Okay. Yes, D is equal to L over 2. But what happens when you square it? It becomes L squared over 4. And so that's where it goes. So let's do something. I mean, and you could do bizarre things with this. You could figure out what a disk is rotating about its edge. Well, let's find this out. Using the parallel axis theorem, the moment of inertia about a disk about its center of mass is 1/2 mr squared. Plus md squared. Well, what is d in this case? What is the distance from the center of mass of the disk to the rotation point? It's the radius. That's all it is. So the moment of inertia of a disk rotating about its edge, one of its points, is 3/2 mr squared. And so parallel axis theorem, to calculate moments of inertia, you can do it fairly quickly once you understand what that D represents. All right. So we've covered, let's go through this. So we've gone through position, velocity, acceleration, angle, angular velocity, angular acceleration, moments of inertia. So we could do some basic rotation problems, and we're going to add some more identities along the way. Let's first study simply, we have a disk and it's rotating. It's constant rotation. So it's not speeding up or slowing down. And let's take a look at what's going on. If I was to say, what is the velocity of a point at the edge of the disk at that location, the velocity vector looks like that. If I said, well, what is the velocity vector for a point out there? It looks like that. And so on. If at any point the velocity vector is parallel to the surface of the circle at that point, it is also perpendicular to the radius going out to that point. So we have these velocity vectors, and the velocity vectors are changing. The velocity vectors are changing. So if you have a changing velocity, what do you have? And you have an acceleration. The linear velocity is changing. So AR exists. AR stands for radial acceleration. It's the linear acceleration on a point on a moving or a rotating object. So if you have an object that's rotating, there are points on that disk which are moving in all sorts of different directions. And that point at one time is going straight up. Another time it's going straight left. Another time it's going straight down. So it is accelerating. This acceleration is called radial acceleration. AR is not alpha. This object, we're currently having it rotate at a constant rate. So it's d omega dt, its rotation rate, is equal to 0. But AR is not equal to 0. If that thing's rotating, that AR is non-zero. The only way that AR can be 0 is if the disk isn't rotating at all. Now to draw these, let's draw a bigger circle. Those radial acceleration vectors are all pointed inward. So if you have a point here, its velocity is to the left and its radial acceleration is straight down. The V is always perpendicular to AR. AR is always perpendicular to V. And the relationship between this linear velocity and the radial acceleration is that radial acceleration is equal to v squared over r. So if the v at that point was moving 3 meters per second and the radius was 4 meters, the radial acceleration that this thing would experience is 3 squared over 4, or 9/4 meters per second squared. The other thing that you notice is that radial acceleration is a linear acceleration. It uses meters per second squared. V squared is meters squared, second squared. R is in meters. And I'm left with meters per second squared. And so you get this. Now, what we typically mean by, it's a dangerous word, radial acceleration, because it can talk about certain things that don't truly exist. If you've been on the one that I was on, it existed before Katrina took it out. The Cajun Land, Six Flags on in New Orleans. The Gravitron, and what the Gravitron is it's a big disc with a wall all the way around the edge of the disc. You walk in that area, put your back up to the wall, and it starts slinging you around. Well, what you're feeling is the acceleration of that wall on you, pushing you forever inwards. And in linear motion, the sum of the forces is equal to ma, and in rotational motion, sum of the forces is also equal to ma, but in rotational motion, a is v squared over r. This a is the radial acceleration, so we rewrite it as mv squared over r. So if you have rotational motion going on, the relationship between the forces on that particle and its velocity and its mass and its radius is mv squared over r. This AR here, what we typically, well, I mention it because I'm a fan of Top Gun. In Top Gun, they're always talking about, oh yeah, I pulled a 4G turn and stuff like that. Well, what does that mean? That means his radial acceleration was 4 times that of gravity. A G is equal to 10 meters per second squared. We're all experiencing 1 G of gravity right now. We're all experiencing 10 meters per second gravity right now. If you were to experience 2 G's of acceleration, you'd do fine. You'd do fine at 3. At 4, we'd start having problems. If the problems that fighter pilots have when they're doing these dips and turns is that the acceleration is so great that the blood is draining out of their head, and at 6 G's they tend to black out. So it's you start to having to consider physics of the fluids inside you when you're making these rapid turns. And if it's over 3, start worrying. These rotating objects have other terms that we need to think about. If a disk makes 1 turn every 5 seconds, its period is 5 seconds, or t is equal to 5. Period t is the time for one rotation. So if it takes 2 seconds to rotate, its period is 2. If it takes a tenth of a second, its period is 1/10. Very straightforward. Its frequency is 1/, period. Frequency is just the inverse of period. Frequency is the number of rotations or oscillations made per second. So in our particular case, its period was 5 seconds. So its frequency is 1/5 seconds. So it is 0.2 inverse seconds, and 1 inverse second is a hertz. So we can change that to 0.2 hertz. Now, since omega is constant, d omega dt is equal to 0, so alpha is equal to 0. So in a situation where there is no change in angular velocity, the alpha is 0. If there was a change in angular velocity, the alpha will not be 0. In the test, so on the test, there will be a rotation problem. They fall into two typical categories. It will either be alpha equals 0 or alpha not equaling 0. It's only two types you got. If alpha is equal to 0, the one not covered on the test will be on the final. Physics is a rather broad subject. I only have, now granted, you do have 2 hours to take the test, but even then that's still not enough time to cover everything that I really want to cover. So what I typically do is there are two types of rotation problems. One where alpha is 0, one where alpha isn't 0. The moment you look at that test and go, oh, alpha is 0 on the test, therefore I know alpha will not be 0 on the final. Kind of lets you know. This angular velocity omega is 2 pi f. So if I give you the frequency, which in this case was 0.2 I know for a fact that this thing is rotating at 1.26 radians per second. The typical unit, the standard unit that rotation uses is radians per second. Doesn't use degrees per second. In rotation, the numbers that you plug in have to be in radians. Now, a lot of people showed some concern on test 1 about do they use radians or degrees when they're plugging in sine and cosine. In test 2, you're not going to be taking sines and cosines. Everything will be expressed in radians, and you just go through that way. You just treat radians per second just like a number, like you do anything else. And a part of me, when I first started studying physics, I was like, how am I supposed to remember omega equals 2 pi f? Well, ask you a few basic questions. How many radians are in a circle? 2 pi. If you have a frequency of 1, you're making 1 rotation every second, which means you're making 2 pi radians every second. Which means that it should be 2 pi f, because when f is 1, omega has to be 2 pi. It just has to. So omega is 2 pi f. You could also say that omega is 2 pi over t, but I tend to remember that one and just go from there. So if this thing is rotating and you have a frequency, you can figure out its angular velocity. The other thing that you can do with this, let's say the disk that we've been talking about has a radius of 0.4 meters. And I know what its omega is, it's 1.26. What is its velocity that you can get off of this? The relationship that you need is V equals omega R. Or use big R in this case, since we're using big R. To get the linear velocity of a point at a specific radius R, you multiply omega with R to get its linear velocity. So this is 1.26 times 0.4. And I get 0.50 meters per second. And I've got the numbers sitting in my calculator, so it's a little bit more precise. And so you can get numbers like this. And so with all of this stuff, you can do all sorts of things. Going back to adding a little bit more on our Rosetta Stone. In the linear world, we have momentum, P, which is mv. And P is momentum. And it has a units of kilograms, meters per second. Well, in the rotational world, we have something called angular momentum. Angular momentum is capital L. And capital L is equal to I omega, and which means that it has units of kilograms, meters squared per second. And those are the units for angular momentum. Now, just as conservation of momentum. Conservation of momentum, you have the initial momentum is equal to the final momentum. It's very handy for collisions. Angular momentum, you have conservation of angular momentum. And that means that L initial is equal to L final. That the angular momenta remains the same. Now, what's the best way, or what's the most common way that we can think of about conservation of angular momentum that we've all seen? Well, hopefully that door still opens. You've all seen like ice skaters. And if I can't find it in 30 seconds, I've got to walk back. Or someone. All right. When you've got an ice skater and they spin on their tippy toes, they've got their arms out. What happens when they pull their arms inward? They speed up. Well, they have the same amount of energy that they had before. By them pulling their arms inward, they have changed the distribution of their mass. So change in the distribution of their mass changes their moment of inertia. To draw this thing out a bit, that equation must be true. So if I final goes down, then omega final goes up. Now, the best demonstration for this, or the best thing that I would recommend that y'all do, if you go on YouTube, you can find a demonstration of this, is you get, let's say this disc has and I'm going to try to do it legitimately, has a radius of 2 meters. And the mass of the disc is 100 kilograms. And I want initially, this is the thing I'm going to make different. I want the AR of this thing rotating initially to be 4 meters per second. Half a G, a little bit less than half a G, is entirely legitimate in order to hold on. It's not that big of a deal. So if I have a radial acceleration of 4 meters per second, what is the linear velocity of this particle at the edge? Well, AR is equal to V squared over R. So AR big R is equal to V squared, or V is the square root of AR R, which is the square root of 4 times 2. So square root of 8. So 2.83. So it has a linear motion for those particles at the edge of 2.83 meters per second. Now the next question would be well, what is the omega? And what is the frequency of this disk? Well, omega V is equal to omega R. So V over R is equal to omega. So this means that we have 2.83 divided by 2. So my omega, and I'm keeping the numbers in the calculator so I can get accurate answers. So this is 1.41 radians per second. So we can ask another question. Well, what is the frequency of this rotation? If I know this is 1.41, I know that 2 pi f is equal to omega. So f is omega over 2 pi. So 1.41 over 2 pi gives me a frequency of 0.225 hertz. And the period of this motion .44 seconds. So this disk is rotating with the period of 4.44 seconds. In reality, there are 4 people on this disk. I'm going to treat them as point masses. So 1, 2, 3, 4. The mass of each person is, let's just say 80 kilograms. I don't know if that's heavy or not. But let's just assume that they are. And the next question that I could ask, and really just taking a moment back and explain what I'm doing. The rotation problem is a lot like this that's going to be on the test. You're presented with a situation and then I just ask tons of questions. Where in the 2D motion problems, in the vector addition problems, there is a very rigid procedure in order to do this. With rotational motion, it gets a little kind of like freestyle, where you've got a lot of equations and you just start piecing them together slowly until you complete the picture. The angular momentum is the total moment of inertia times omega. Now, moments of inertia add like masses. So if I have a 1 kilogram mass and a 4 kilogram mass and I put them together, how much mass do I have? Answer 5. Why? You just add them together. You do the same thing with moment of inertia. This total moment of inertia is 4 times the moment of inertia of one of the point particle kids plus the moment of inertia of the whole disk. So you just add them together. These are identical kids. So this is 4 times mass of the point, r squared, because they're on the edge of the disk, plus 1/2 mass of the disk, r squared. Moments of inertia of point particles, mr squared. Moments of inertia of disks, 1/2 mr squared. So this gives you 482 squared plus 1/2 102 squared. And I'm left with $1480. Kilograms meters squared. So that is the total moment of inertia of the system. And if I asked, well, what is the, what's the angular momentum of the system? You would just take that 1480 and multiply it by its omega, 1.41. And you get 2086.8 kilograms meters squared per second. And so that is the angular momentum of the system. Yes?
On the, where you got the 1480, why didn't you use 100 as the mass for the second one?
Because the mass of the disk, as stated, was 100 kilograms. So that was it. Why? Because I said so. So, now you can do this. Go down to your local playground, find the little merry-go-round thing, and what you do is you get 4 kids to stand at the edge on the merry-go-round and have it go around at a particular frequency. 3 of you will be on the joke, or with the joke, know what's going on. The 4th person has no clue that you're about to do this. The 3 of you, you leave that poor kid out at the edge. And what did I say the radius of this thing was? 2. Make it a legitimate distance. The other 3 move towards the center where that new R prime is 0.5 meters. So one of the kids is out there at 2 meters and you move to 0.5 meters away. Just like the ice skater, the merry-go-round is going to speed up. So the question is, on this poor soul out here on the edge, what is their new radial acceleration? Yes?
Can I see the end of that?
Sure. So what's the first thing that we got to do in order to calculate this? We got to find its new moment of inertia. The mass distribution has changed. So I total prime is now 3 times the mass of a point times R prime squared plus 1 times mass of a point R squared plus 1/2 mass of the disk R squared. This becomes 3 times 80 times 0.5 squared plus 80 times 2 squared plus 1/2 100 times 2 squared. And that gives us oh goodness. It gives us 500. Do the math on this. Hold on. I don't trust this. Because this kid's about to get flung off. So the new moment of inertia is 580 kilograms meters squared. It's okay, so it's only about 1/3 of its original value. So it went from 1480 to 580 kilograms meters squared. Let's calculate its new angular velocity. Angular momentum is conserved. The new angular momentum is the same as the old angular momentum, which means it should be 2086.8. So L is equal to I prime omega prime or omega prime is equal to L over I prime. So L, 2086.8, I prime, 580. Its new omega prime is 3.60 radians per second. That is its new angular velocity. Well, if its new angular velocity is 3.6 radians per second, well, what is its frequency? Well, 2 pi f is equal to omega. So f prime is equal to omega prime over 2 pi. Notice how the same equations are keep being used, recycled over and over and over again. Omega is 3.6, 2 pi gives us 0.57 hertz. And if the frequency is 0.57 hertz, then the period is 1.75 seconds. So the frequency was initially 0.225 hertz. Now it's 0.57. The period was initially 4.4 seconds. Now it's been cut more than half. It's now down to 1.75 seconds. Now, radial acceleration is v squared over r. And what I'm going to show you is I'm going to start doing some substitutions and doing something a little bit more alpha soup mode-ish. If the radial acceleration is v squared over r, v is omega r. So radial acceleration becomes omega r squared, which is omega squared r squared over r. So radial acceleration is omega squared r. And so that's kind of an identity. Well, I have my omega, 3.6 squared. R is 2. And I get 26 meters per second squared. Now let's talk about this for a moment. Initially, the radial acceleration was 0.4, or I'm sorry, not 0.4, 4 meters per second squared. Everybody could handle, like if I turned off gravity and said everybody just hold on to the ceiling and I put a gravity of 4 meters per second on you, you'd be able to hold on. That's lighter than gravity. That's no big deal. But when these kids pull towards the middle, the disc spins up. Now the kid at the edge goes from 4 meters per second to 26 meters per second. If I told everybody to hang from the ceiling and put 26 meters per second acceleration on you, most of you would just fall right off, including that kid. He would be slung off of it, hit the dirt, everybody would laugh at him, and then you let some other kid get on it and then repeat the process. And so that's how it goes. So this is a great demonstration of working with rotational motion where alpha is equal to 0, and conservation of angular momentum. There are going to be problems. We're going to have to deal with this. And then the big thing about it is it's very similar, and I gave it to you Did I give it to you this time? Oh, I gave it to you on the next problem set. The fish of fury problem. In the problem set that is handed out tomorrow, you're going to do the fish of fury. The fish of fury is the standard rotation problem where alpha is equal to 0. It's basically like this. And you'll be able to do that. Trying to see if we've got everything that we need to do. Oh, okay. So what I'm going to do is, let's see, how am I going to divide my time? All right, let's talk about, never fails, let's just talk more about Atwoods machine. In fact, what I'm going to do is, for on this particular problem set, what you notice is this is 1 through 8, 9, and 10 are a whole bunch of rotation problem. Hold on. Yeah, okay, that's fine. And then we've already covered all of this. And on the back are 2 more rotation problems and these 6 guys. And you notice that they look very familiar. They look exactly like the problems that you did in problem set 2. I want you to go over these 6 problems with only this. You're only allowed to use the equations of energy, and you're only required to determine the velocity at the bottom of these hills. So here, they're all the same initial velocity, 3 meters per second. These are all the initial velocities of 0. They all have the same coefficients of friction and angles. You have to calculate the final velocity. And what I'm going to do is I'm going to do number 12, and I'll do number 15, and show you what should happen is that the final velocities that you get for these 6 problems are going to be the same as the final velocities that you get in problem 2. In problem 2, or in problem set 2, in problem set 2, you had to go through a huge procedure of covering forces and tensions and motion and all that. With this, just energy. And you'll see why it's way more efficient. For number 12, you write this thing out. There are 2 states that I only care about. The initial state has a height h and an initial velocity of 3 meters per second. It slides down an inclined plane where that length is 3.3 meters. The theta is equal to 20, and the mu sub k is equal to 0.4. I have to find the velocity at the bottom. Now for this, we do have friction, boo friction. So we do have to find the friction force. That's the normal force, that's the friction force. The sum of the forces in y is equal to 0. I know that the object is not penetrating the surface or flying off. So we can say that the normal force, or the sum of the forces in y is equal to 0. This means that normal force minus mg cos theta is equal to 0. So Fn is equal to mg cos theta, or friction force is mu sub k mg cos theta. Which means that the work, which is the friction force times distance, or in this case it's L, is mu sub k mgl cosine theta. I switched the d to L and the f sub f to mu sub k mg cosine theta. So that's the energy removed through friction. This problem is set up such that we use the checking account equation. The energy initial minus the energy removed through friction is the energy final. Energy initial, well, that's just the potential energy. The final energy is kinetic. Oh, I forgot one thing. There is a kinetic energy initially to begin with. The thing is initially moving at 3 meters per second. If it's initially moving at 3 meters per second, there is a kinetic energy term initially. The kinetic energy initially is 1/2 mv naught squared. The potential energy, well, potential energy is a little bit different. Potential energy is mgh. We don't know what h is. However, we can solve for it. If I know the length and I know theta, I know that sine of theta is h over L. So L sine theta is equal to h. So the potential energy is equal to mgl sine theta. So there we go. Minus the work removed through friction, so minus mu sub k mgl cos theta is equal to 1/2 mv final squared. There's no potential energy at the end, so all we have to do is just write that out. What we notice is that there is an m in each of the 3 terms, so if I factor out an m, I know, it's a long. Those m's cancel, and so it's not necessary to know the mass of the object. I'm going to multiply by 2 just to get rid of the fractions. And I get that. And then square root it. And I'll treat this like a tutorial, so I will let you plug it in. But basically all you have to do now is plug in all the values and then you got the answer. Now what happens like in problem 11 where you have no friction? Mu sub k is 0 and that goes away. And then effectively I've done problem 13 for you because it's the same setup but different numbers. So understand how this problem is assembled and then you can get everything that you need to do. Problem 15, I've been telling kids this for years. Problem 15 is going to be on the test. You're going to have, what have I always said? Everyone is going to have an Atwoods machine problem on every single test and on every final till we all get it right. Which means that when the sun burns out, I'll be giving a test and that Atwoods machine will still be on it. We will be doing this forever. With a problem like 15, it's important to understand the beginning and ending conditions. The beginning condition, no motion. It's all potential energy. Now, when we think about potential energy, the only potential energy that I'm caring about in this particular problem is M2. M2 is falling and hitting the ground. Why do I not consider the potential energy of M1? It's on the surface. It does not change its height. So if it doesn't change its height, its potential energy is not contributing to anything. So its initial potential energy, its initial energy is equal to M2GL. Its final potential energy, or its final energy, excuse me, is 1/2 M1 plus M2 V squared. The velocity of the objects are moving is 1. It's as if it's just one object with a combined mass of M1 plus M2. Since they're moving in a combined fashion, their total kinetic energy is 1/2 times the sum of the masses times V squared. There is a mu sub k. And if that object falls distance L, then that object moves distance L. Now, we just got done doing the derivation of figuring out what work is. So we would go through these steps to get, to get this, but cosine theta is 1. Might as well do it anyway. Sum of the forces in y is equal to 0. So this is normal force minus mg. So normal force is equal to mg, which means friction force is mu sub k mg, which means the work done through friction is that, which means that we get mu sub k mgl. Because if it falls distance L, then the d in this work equation is also L as well. So putting all these parts together, M2GL minus mu sub k, oh, and this is M1. Mu sub k M1 GL is equal to 1/2 M1 plus M2 V squared. And so that is the energy equation for the motion. Now, in the test, this is the setup that you got to do. It's a lot easier than doing Atwoods machine with motion to find velocity. If I had to figure out the time that it took for it to fall, I would use motion. If I had to find final velocity, I would use energy. Solving for V, 2 over M1 plus M2 I'm going to factor out some common terms. 2GL over M1 plus M2. M2 minus mu sub k M1 is equal to V squared. Which means that the square root of 2GL over M1 plus M2 minus mu sub k M1 is equal to V. And so that's it. That's the solution. You should be able to take that equation here, be able to derive it, and then be able to solve for any variable that I ask for. Will there be a substitution, a crazy substitution like M1 is 1/2 of M2? Perhaps. You should be ready for it. It's not a big deal. You should look at this and solve for every single variable. And if you can go through this, get there, solve for every variable in this equation, you're set for the problem. Done. Yes?
This is kind of a dumb question, but if you did say like m sub 2 is like 2 times m sub 1, but you don't give us m sub 1, how do you find that?
Okay. If I, in the, I need English in my head. Remember in test 1, I asked, originally that Atwoods machine, I asked for tension, and then I made the announcement that I'm not asking for tension, cross it out. Because I gave you a mass ratio. Because I gave you a mass ratio, finding the tension became impossible to determine. So if I needed to give you, if I needed you to give me tension, I would have to give you the mass. So in a problem like this, if I gave you a ratio, okay, I know what you're asking. If I gave you a ratio of masses and asked you to give me one of the masses, you couldn't do it. I wouldn't ask you for that. If I did ask you to find M1, I would have to give you M2. And then you could just calculate it straight out. It's one of those things where you have to follow rules, I have to follow rules. So if I specifically asked for M1, I'd be required to give you M2 because then it's numerically impossible if I didn't. Or I'd have to get cute with another substitution. I don't know. One of the things that we could look at here is, let's do a unit check and see if this equation right here makes any sense. G, meters per second squared. L, meters. M1 plus M2 are both kilograms. Kilograms plus kilograms is kilograms. M2 is kilograms minus mu sub k kilograms. So that gives you kilograms. Cross, cross, and I'm left with the square root of m squared over second squared, which is meters per second. So the units do check. And so when you do a problem and see something like this, and you do a unit check for it, and it works out, you've got confidence. You can sit there and go, this is a good equation. Something that you cannot do with plug and chug. Plug and chug are very difficult to diagnose what you guys did wrong because it could go anywhere, and if I can't do a unit check, I can't figure out really what the problem is. So that's 12 and 15. And I think that's all the stuff that we need to do. So we'll do one last problem and then I think we'll call it a day. Oh, we could do this. I know exactly, okay, done. I know exactly what we're gonna do. I'm sorry, having a little conversation during class. Eschenberg students know how to do several things. 1, add vectors. 2, do 2D motion. 3, they know not to use conservation of energy in an inelastic collision. And 4, and this is something that we're going to use tomorrow, and it will be on the problem set handed out tomorrow, you guys know the right hand rule. Now really what we're doing is we're taking two vectors and we're doing, in math terms, it's called a cross product. Now a cross product, what was really interesting, a cross product is I'm going to say it in math. I know you guys are going to look at me and go, what? The cross product is taking a 3x3 matrix and finding its determinant. No one in the room knows what I've just said, which is okay. It's fine. But what the right-hand rule does is it replaces all this mathematical complexity with your right hand, and it effectively turns your right hand into a little bit of a calculator. The right-hand rule on the test for the appetizer, you're going to play the right-hand rule game. And what happens is you see a setup like this where these directions are labeled. So B in this case, if we're looking at just that screen, B is towards the ceiling, D is towards the observatory, F is towards the library, E is to the ground, and we're gonna develop this a little bit more in terms of complexity, but the first lesson that we gotta do is you all see A and B, or A and C. A is a circle with a dot, C is a circle with the crosshairs, and in order to best demonstrate what these are and how I remember. So I'm going to take this is my magic bow, my magic longbow. Take it, I'm going to aim it at your face. So, you're backing away, it's make-believe. So what do you see when I've got my magic arrow aimed at you? The tip of the arrow. So the tip of the arrow is what? It's A. A is the vector coming out of the page. A is the vector coming at you in this particular case. If you got control of my magic bow and arrow, which I doubt it, but if you were able to get it, what would you see now? The X, the fletching, the arrow, the feathers. So C is the arrow headed away from you. C is the arrow going into the page. So coming at you, tip of the arrow. Going away from you, the feathers. Now the right-hand rule game, I've been trying to teach my niece, she'll be 9 in December. I've been trying to do this since she was 2. Wasn't very good at 2. But she was able to master the motion of what you do with the right-hand rule. You take, it looks like this. This, that, and that. So I'll show it again to the class. 1, 2, 3. 1, 2, 3. 1, 2, 3. So the first vector is 3 motions. Now I will admit, one person doing this looks kind of goofy. When you get 50 people in a room doing it all together, it looks kind of cool. So the first vector, the A vector, and I'm going to write it out, is first vector. And a lot of you are sitting there going, what's the use of this? It will be used for something called torque, and we'll do that tomorrow, torque or rotational force. For those of you continuing on to 214, the right-hand rule will be used for charged particles and magnetic fields. So it is a very useful thing to have. The first vector, palm and fingers point in the first directions, or the first vector's direction. So notice with the first vector, in fact, the way that even I do it is for the first vector, the fingers, palm, and forearm are all in line, the whole thing. The second vector, fingers only curve in that direction. So on the camera, first vector, let's say second vector was that way. First vector, palm, fingers, and forearm are all in a line. And then when I curve, only my fingers bend. So first vector, second vector. The third vector is thumb naturally points in third vector's direction. So the first vector, let's say it's in this direction. Second vector, that direction. The thumb naturally points at the camera. First vector, let's say, is towards the ceiling. Second vector is towards you, or towards the back of the room. Third vector is like this. So we're going to initially play this game where we're only allowed to think about what's on the screen. So when you write this stuff down, when you're playing the game for today, we're going to play this game again tomorrow, and then we're going to make it a little bit more complex. We're only using the letters here, so kind of ignore that. The purpose of this is to test your three-dimensional perception. D cross A. Now, A will not always be out of the page. F will not always be to the right. I can change the letters. I can change the letters to words. It doesn't really matter. What does matter are the directions. So what we're going to do is we're all going to look at the board, and we're going to do the first one. B cross F. So B is towards the ceiling. F is that way, which means that my thumb naturally points into the board. And into the board means what? C. So B, F, into the board, or C. Now, in the second one, I've got B cross F, or I'm sorry, F cross B. The thing that you need to know is B cross F is not equal to F cross B. I mean, you could say, we all know A plus B is equal to B plus A, but A cross B is never B cross A. So in this case, F cross B, F towards the right, B towards the ceiling, out of the page, or A. And what you learn is that F cross B is equal to negative B cross F. That if you swap the order of the vectors, the vector direction changes. Now, one of the things that I can show, if we did B cross F again, the way that my hand is organized, B is towards the ceiling, but F is this direction. And you notice how my fingers can't bend in that direction. Now, granted, there was a girl a couple of years ago in that chair. She was double jointed, and she just flopped her hand over, and it freaked me out. I'm like, you were hurt as a child for some reason. So if I can't bend it in that direction, this is an allowable move. I can rotate the whole fingers, palm, forearm, and rotate it, and then now I can go in that direction. So first, second, third. C cross D. C is into the board. D is that direction. So the answer is towards the ceiling, which is B. Now, a couple of rules about the right-hand rule game. I will never give you A cross A. You cannot cross something. It's mathematically possible, but I'm not going to give you a cross with itself. I'm also never going to give you a cross with a vector that's 180 degrees around. So D cross F, A cross C, B cross E are not allowed. I won't give you that, but I'll give you everything else. The other thing that we need to look at, it really doesn't have to be the same orientation. Well, right now I've rotated it 90 degrees, and let's work with that. The third problem, C cross D. In this particular case, C is into the board like it was before, but now D is towards the floor, which means the thumb points this way, which again is D. So it doesn't matter about the orientation of the paper. What does matter about the orientation of the paper is you can't go, all right, first vector and then rotate the page. You can't rotate the page during the calculation. You have to keep it constant. And then once you move to the next problem, then you can rotate it. But if we took this paper like this, like that, like this, you would get the same answer. But you just have to remain consistent with where you're pointing during each of the problems. All right, last two. A cross E. I've already done it. Let you figure it out. A cross E. It is F. A is out of the board or towards the back of the room. E is towards the ground, which means that's pointed at. And then our last one, D cross A, is what? B. D towards that wall. A out of the board points towards the ceiling, which is B. Now, what we've covered today is this problem. Atwoods machine with energy will be on the test. What we have done just now is the appetizer of the test. So we've already covered two of these. I've already posted 2 sample test 2s that you can go and take a look at. All right, thank you.